So we have put together some ideas about the process of vaporization, but let's think about if we had some kind of insulated container, kind of looks like the cross-section of our coffee cup calorimeter, but I won't double the insulation, we just need a little bit. And you have a liquid sample. Right, so these are all my liquid molecules, and they are vaporizing at whatever rate they do, depending on the temperature and their intermolecular forces. So this is going to be some insulated container with an open top. And my question is, what happens to the temperature as the molecules vaporize? So you could stop the video if you want to take a minute, although I know some of this is going to be kind of popped up on the screen. But if we have this sample that has some average kinetic energy, and you take away a molecule that had a high kinetic energy because it had enough to escape the surface, now your sample has a lower kinetic energy. So the temperature has to be lower based on kinetic molecular theory. All right, so I should write that. Based on kinetic molecular theory, the temperature would decrease as the kinetic energy average decreases. The other way that you can think about this, and it's the temperature goes down regardless, vaporization is endothermic, and we have seen this with our phase change stuff already. Right, you have to put in energy to break the intermolecular forces. So that molecule of water that escapes, you can think about it taking energy away from the water sample. And so when you remove it as thermal energy, the temperature goes down. So vaporization is endothermic. The opposite process, condensation, is exothermic. So we use, and as you have seen, this delta H of vaporization is the heat required to vaporize 1 mole of liquid to gas. So at 100 degrees, which is the boiling point of water, taking liquid water to a gas, the delta H of vaporization, it's endothermic, so it's positive. It's 40.7 kilojoules per mole. And I think in some places you'll see it 40.6, depends on how you round. Either way is close enough for us. So if you are at 100 degrees still, H2O gas turning into H2O liquid, the delta H, it's still vaporization. We just reverse the process, so we change the sign. It's negative 40.7 kilojoules per mole. And this negative 40.7 kilojoules per mole for condensation, this is why steam burns are so damaging, right? If you have steam that condenses on your hand, it just in the condensation process gives off 40 kilojoules of heat. And then you still have water at 100 degrees that's on your hand, because the temperature doesn't change when you do a phase change. And so then that water gives up a bunch of thermal energy to the same tissue. So that's why steam burns can be so dangerous. The actual value for the delta H of vaporization depends on temperature. So if we were at 25 degrees, getting water to evaporate, and that is at 25 degrees, ripping those molecules apart into gas molecules without increasing the temperature first. The delta H of vaporization is 44 kilojoules per mole. Oh, that's a 0.0. So the molecules have to use some of the energy to increase their kinetic energy before evaporating. And so it takes just a little bit more to boost them up. So we can use these values just to look at heat transfer between two things. So I'm going to pause this video, write out a problem, and then we'll be back in a sec. So this problem says, suppose 0.48 grams of water at 100 degrees C condenses on the surface of a 55 gram block of aluminum, initially at 25 degrees Celsius. If the heat released during condensation goes only toward heating the metal, what is the final temperature of the block? So we have some block that's going to absorb all of this heat that's given off by condensation. And we know how to calculate a temperature change with heat absorption, right? We have a specific heat capacity. So my metal block, whatever amount of heat it absorbs, right? If I know the mass, if I know the specific heat capacity, and I'm going to be looking for the final temperature, but that's built into my delta T. Right, the thing that I'm solving for, label that, trying to find T final within my delta T. I can do this. We have done this before. The Q part, well, I can only have one unknown, really. So the heat, I have to figure out where that comes from, and it all comes from the condensation. Now, we do have enough information. We've just not explicitly done anything like this before. The heat from condensation, well, I know it will give off, right? It's exothermic, negative 40.7 kilojoules per mole for condensation, which is going to turn into a positive, right? When I go to absorb it into my metal. But before that, if I know how much water I have, in moles, I can figure out how much heat is given off, because this is just like a delta H that goes along with a balanced reaction that depends on the amount. Well, I kind of know. What do I have? 0.48 grams, and I know how to convert grams into moles. So my 0.48 grams of water, well, 1 mole of water is 18.02 grams. So I'm in moles of water, and 1 mole gives off 40.7 kilojoules. So that's negative 1.08 kilojoules of heat given off. So Q for the metal should have the same magnitude, but an opposite sign. So Q for the metal equals negative Q of condensation, which, right, this Q from condensation, it's just my delta H, because delta H is heat at constant pressure. So the heat absorbed by the metal is positive 1.08 kilojoules, which I'm going to make into joules because it'll match the units for our specific heat capacity. All right, I have Q, I have M, I have C, and I have my initial temperature. So my positive 1080 joules equals 55 grams times 0.903 joules per gram degree C times T final minus T initial. And after some algebra, which you should pause, take the space to practice and see if you get the same answer, the T final is 46.7 degrees C. So this makes sense. It's a higher temperature. We were expecting the block to heat up as it absorbed heat. So it would end up at a higher temperature. And that's a lot of heat that was given off by the water condensing. So going from 25 degrees to 46.7 seems like a reasonable change.